Hello, everybody. Welcome to lesson 4. So I'm just going to quickly, for everybody who missed the last lesson, go over a definition because that definition is actually pretty important. So yeah, share screen, that one, share. Can everyone see my screen? I need to turn on chat. No, this is the same room, just a different camera angle. The windows are closed. So, okay, so, no, don't do that. Sorry, geez. Ugh, no, done. All right, so where did chat go? Ugh, chat. There we are. Okay, so people who missed, this is more just for you. So this is just a quick reminder what a simultaneous game is, and you represent it in the form of a game table. So does everybody, so basically, if player A chooses, let me turn on my nice pointer thing. If player A chooses top, then player B, player A can choose top, center, or bottom, and player B can choose left, middle, or right. And then whatever they choose, like if player A chooses top and player B chooses middle, then the intersection is what occurs. So does everybody who missed understand this? I'm going to go through this pretty briefly. So so if nobody says anything, I'm just going to move on. So if you missed and you're not confused, just speak up. All right, so again, if player A chooses top, player B chooses middle, then they overlap at this area, and payoffs are 1 for player A and 0 for player B. So then we have to define what the Nash equilibrium is. So the Nash equilibrium is a stable state of a system involving the interaction of different participants in which no participant can get a unilateral change of strategy if the strategies of the others remain unchanged, which is just a nice way of saying that is neither player would rather switch their strategy to another one as long as the other player stays with their current strategy. So let me just demonstrate what that really means. So in this specific game table, so what this means is that suppose player B is going to stick with left, then if player B switches from top to anything else, then as you can see, player A does not stand to gain anything, right? If he switches from top to center, he goes from 1 to 0.9, and if he switches from top to bottom, he goes from 1 to 0.8. And similarly, if A is going to stick with top and B changes from left to anything else, from left to middle, it goes from 1 to 0, and from left to right, again, 1 to 0. So yeah, that's what Nash equilibrium is. Does everybody who missed it get that? Again, okay, yeah, I'll explain it again. Okay, so one person gets it, but somebody asked for it again, so let's quickly redo this. So suppose player B sticks with left, right? So I know it's a simultaneous game, but remember, everybody, it's kind of like a thought experiment. Both players are kind of not subconsciously, but just kind of thinking about this before it actually happens. So if player B is going to stick with left, really? Okay, that's funny. Give me a sec. Can you hear me now? Is that louder? I don't know if this is a microphone or not. I don't know how any of this works. Okay, cool. So if player B is going to stick with left, then if player A switches whatever he chooses, then he's going to get worse payoffs, right? So player A's payoff is, in this case, 1, but if he switches from top to anything else, he decreases from 1 to 0.9 or 0.8. So clearly he doesn't want to change. And then player B, similarly, if player A sticks with top, and if player B changes from left, middle, or right, if player B switches from left to middle, then it's from 1 to 0, and if it switches from left to right, then it's 1 to 0. So And just to show an example of what's not Nash equilibrium, in this case, as you can see, suppose we just selected this, but it's in player B's best interest to switch from middle to left. So yeah. Okay, yeah. So I'm getting some O's, which is good. I'm going to assume we're done. And that was fast. That's good. All right. So that was a good, give me a second. Let me turn on chat again because this, more chat. Thank you. Okay. So now with that brief reminder about what simultaneous game is, let's go over mixed strategies. So in our the example we just went over with Nash equilibrium, I mean, there was a Nash equilibrium, right? And if, again, so yeah, in that case, there's a mixed Nash equilibrium. So both players had what's called a pure strategy. And that's just when both players know exactly what they're supposed to do, right? So as long as players have one or more Nash equilibria, then they have what's called a pure strategy. So clearly, yeah, this is when there's no Nash, exactly, yeah. So let's get into it. So let's look at this game table, right? Can everybody who I taught how to find Nash equilibria confirm that there is no Nash equilibria in this table, just to make sure everybody remembers? All right, I'm getting a lot of yes, which is good. All right, so clearly there's no Nash equilibria. So what do we do, right? If there's a Nash equilibria, it's very obvious. You know, you just choose the thing where the Nash equilibria is, and that's what you go with. But because there's none, now players are kind of in the dark, right? Well, that isn't, so what should players do? Well, they should just be choosing options with specific probabilities. So does everybody understand? Actually, we'll get there in a second. So that probability should be calculated such that expected outcome is maximized. So basically, players should be choosing their specific options with specific probabilities in order to maximize payoffs. So remember, players just want the most payoffs. So let's go into it. So does everybody understand this like form of probability? Right, all right, so I'm seeing some maybes, so let me just quickly explain it. So we are going to denote some probabilities, right? Because there's no Nash equilibrium, both player A and player B have to alternate between their two strategies. Player A is going to choose up sometimes and down sometimes, and player B is going to choose left sometimes and right sometimes. So we denote the chance that player A chooses up as P. So P is just going to be some number from 0 to 1, and it's just a percent, right? If P is 0.25, then player A is going to choose up with 25% chance. And then that means that 1 minus that, it's just 100% minus that, right? So in this case, in our previous example of P is 0.25, then 1 minus P would be, 1 minus P is the other part, exactly. So this would be 0.75 or 75% chance. If you're having trouble, just think about them like percents, right? And exactly the same with Q. Player B can choose left with Q chance or 100 times Q percent. Wait, no, never mind that. Or just like if Q is like, 30, 0.3, then left is with 30% chance. And right is just 1 minus Q or 100 minus Q like as a percent. So if we say that Q is 0.3, then Q is 30%. Now, Q and P both have to be between 0 and 1, but that's inclusive. So P represents the chance that one player will choose a specific choice. Yeah, P represents the chance player A chooses up, and thus down. 1 minus P represents the choice that player A will choose down. And then left is the chance player B will get left, and right is the chance that player B will choose, 1 minus Q is the chance player B will choose right. So everybody understand that much? I'm getting one yeah, which is good. Is it 1 because there's one other option? Could you state that again, I guess? Yeah, so yeah, the total, I'm assuming you mean total probability. Yeah, so remember, if we convert like this chance, which is a decimal, into a percent, you just remove the decimal, right? So it's 0.25, which then turns into just 25%. Similarly, 1 minus p, 1 becomes 100%, and p becomes like 100 times p percent. So in total, the probabilities of all actions have to add up to 1. And if you're doing it in percent, then it has to add up to 100. So we're going to be using decimals simply because it's easier to do decimals with math than it is percents. So yeah. All right, so we're going to first step in the, not step in the shoes, but like consider player A, right? How should he choose P such that he maximizes his payoffs? Well, we have to calculate what okay. So we have to calculate what player A's expected payoff is, right? So given these probabilities, what do we expect player A to get, right? So this means that we're going to assume that player A knows what player B is going to choose, and then we're going to move on from there, right? So if player B chooses left, then with P chance, player A is going to get a payoff of 5, and with 1 minus P chance, player A gets a payoff of 9. So if player P chooses left, player A's payoff is 5P plus 9 times 1 minus P. Does everybody understand this? Because we don't know what P is, but we're going to have to figure it out, right? It's just an expected value. Once we know what P is, we can calculate what A's expected value is. Does everybody understand what expected value it is? Okay. I'm getting yeses. So yeah, just everybody gets expected value. I'm good. I'm going to assume yes, and we're gonna move right on along. No. Remember, Prisoner's Dilemma has a Nash equilibrium, so this isn't an example of that. Did you see the, were you here at the beginning of class today, or were you here yesterday? No, Calvin. But were you here at the beginning of class right now? No, it's fine. I'm just wondering if I should quickly go over it again. This will be super quick. I'll just show you the quick definition. All right, everybody, just give me a moment. This will take 1 second. I just want to make sure everybody's on track. No, you're fine. It's quick. This will be fast. I'm just going to show you this slide. Yeah, so as you can see in this slide, so if you remember what a simultaneous game is, as you can see, player A can either choose top, center, or bottom. Player B can choose left, middle, or right. If player A switches from top to, if player B sticks with left, and then if player A switches from top to center or top to bottom, he stands to lose payoff, right? So it's not good for if player B sticks with left and player A switches, then it's not good for him. And the same is with player B. If player A sticks with top and player B switches from left to middle or right, then player B is going to lose payoff. So it's kind of a state of agreement. Because XKCD is funny. I don't know what you're talking about, partner. All right, let's go back to this. Let me turn on the chat again because every time I turn on the presentation. Okay, So back to this. Um, okay, cool. That's good to know. So now we're going to calculate the expected payoff if player B chooses right. So again, with chance P, player A is going to choose up with the payoff of 8. And with chance 1 minus P, player A will choose down with what's the question mark? Why are you question marking? Is there a problem? Okay. Is there a problem at all? Remember that payoffs aren't about like getting more than your opponent. Payoffs, it's just about getting the most payoffs for yourself. You don't care about your opponent's payoffs at all. It's just about, yeah, exactly. So it doesn't matter. So in this case, it doesn't matter that player A and player B tied. Player A only cares that he got 5, right? So yeah. So let me go back to. I guess I don't know, but I'm just gonna go back to this. So yeah, player yeah. Okay, so if player B chooses right, then with P chance, player A is going to go up, get a payoff of 8, and with 1 minus P chance, player A chooses down and gets a payoff of 2. So that means the expected payoff for when player B chooses right is 8 times P, so the payoff times the chance, and then the payoff times the chance, 2 times 1 minus P, right? So now that we have this, we do already know the chance. We already know we don't know what player B's probabilities are, but we have a representation for it, right? The probability that player B chooses left is Q, and the probability that player B chooses right is 1 minus Q. So now we include that into our calculation, right? So now we have the very long equation, but I mean, it's pretty simple to understand in words. So 5p plus 9 times 1 minus p all times q plus 2p plus 8 times 1 minus p times 1 minus q. And that sounds weird and complicated. It's just, so this is if player B is going to choose left with q chance. And in that case, player A is going to choose give me a sec, up with P chance and get a payoff of 5 in that case. The player is going to choose get a payoff of 9 when he chooses down with 1 minus P chance. And if player B goes right, that's a chance of 1 minus Q, remember. And that means that with P chance, player A goes up and gets a payoff of 2. And with 1 minus P chance, player A goes down and chooses 8 and gets a payoff of 8, not chooses. So does everybody understand like what this equation means? Um, can't you solve the actual chance with a lot of time looking at the end results of payoffs? I'm not exactly entirely sure what that means, but we are going to solve the actual chance. Don't worry. That's no. We are calculating what P and Q are in the end. That's the point of this. P and Q, we're trying to solve what P and Q are. So the end goal of this is to figure out with, let me just go back to the slide with this. With how many times out of 100 should player A choose up and how many times should player A choose down, such that, so in the case of mixed Nash equilibria, you are like, both players are pretending, even if the game isn't repeated, they're both pretending that it is, right? Because that's how probability. I mean, that's how probability works. You just pretend. So both players pretend. Okay, let's pretend this game is going to go more and more. How would I maximize this game if it went on? Even if it doesn't go on, that's how this works. So yeah, we can simplify this. But again, does everybody understand this large annoying thing? Because this is pretty important. Like not just what it is, but what it represents. It's just a big probability soup. All right, I see plenty of yeses, so I'm going to move on. So we can simplify this to a nice clean 2 plus 7q plus 6 minus 10q times p. Now what's kind of interesting here is that q, b's probability, appears more than p. We can't use a computer, and I'll show you why. Because we can, but it's kind of weird to do things myself. So I'm too late. Oh yeah. To just simplify this, simplifying this is the simplified version. Take my word for it. I got this example from my textbook, so this is correct. At least this part is correct. I know that as a fact. If anybody points out if I did anything wrong with my math, I'll give you $1 or something. I'll PayPal you like $1. Anyway, so I'll get the textbook and another book which is a bit simpler, but the textbook's a bit complex. But it's a good read. All right, so we have this simplified form 2 plus 7q plus 6 minus 10q times p. So remember, player A can only no spoilers. Player A can only influence q. P. Keep on speaking. Did you switch to 2 and the 8? No, I did not. Yes, I did, but that's not. Don't worry, it's correct. That's just a typo. That's my bad. Again, that's supposed, and that's not a math error. That is that's just a typo. Don't worry, the math is still fine. I know for a fact the math is still fine. That's not great. All right, so notice the interesting point that player A can only influence P, right? But Q is a lot more prevalent in this equation, right? Q is in two whatever. Well, Q is here twice, P is only here once, and A can only choose P, right? So now we have to create some sort of rules for A, because even though he doesn't know what Q is, right? So we have our equation, and we notice the coefficient on P is 6 minus 10Q. So we can create some basic deductions, right? So when Q is greater than 0.6, this value of 6 minus 10Q becomes negative, so P will become 0. So, soup. Okay, so player A is always going to choose down if Q is greater than 0.6. So let's quickly examine why, right? So if Q is greater than 0.6, suddenly this number, 6 minus 10Q, is becoming negative, right? So suddenly player A is losing payoff. So player A is going to say, no, I don't want to lose any payoff that I would get from this section, 2 plus 7Q, which he doesn't actually have, which they don't actually have any control over. So they simply make P equal to 0. So player A is always going to choose down in that case, right? P is the probability that player A chooses up. So now that that's 0, player A will never choose it and will always choose down instead. So when Q is less than 0.6, the value becomes positive and P will become 1. Player A will choose up. So suddenly, we'll get there. So suddenly P, this coefficient, 6 minus 10Q, is a positive number, right? So player A is thinking, okay, that's good. I want more payoff. So I'm just going to always choose up if I know that the Q is less than 0.6. So player A is always going to choose up in that case. So that, remember, this is his payoff, like his expected payoff. So he's always going to choose that. But the interesting part is when Q equals 0.6, player A will always get the same expected payoff no matter what they choose, right? Because suddenly this becomes 0, right? So suddenly, no matter what player A does, it has no bearing on the situation at all. All that matters is this 2 plus 7q, right? Suddenly, player A is just completely, what he chooses doesn't matter. So when q equals 0.6, player A doesn't, he can choose whatever. He can do whatever probability he wants. It doesn't matter. So these are what are called response rules, right? So now player A has a set of rules that given whatever player B's q is, he knows what to set his p to, right? So if it's greater than, if q is 0.6, player A is going to set his p to 0. If q is less than 0.6, p will be set to 1. And when q is equal to 0.6, player A it doesn't matter what player A's p will choose, right? Does everybody understand this? This is a bit of a weird idea, but does everybody understand where this is coming from? I can really quickly go over the math again if you want me to, like 0.6. Just look at the coefficient, right? So we look at so remember, player A can only choose what P is, and he has no bearing over Q. Q is player B's probability of choosing left. Go to the last slide so I can screenshot. Here. You good? Okay. So let me return, so the 0.6, so remember, player A only has bearing over P. Q is entirely player B's control, and player A can't do anything about it. So we focus on this coefficient of P, 6 minus 10Q. So when, and then you can see it. So when, if you plug in, suppose you plug in 0.7, right? So 0.7 times 10 is 7. So 6 minus 7 is -1. So suddenly player A's expected payoff is decreasing. So he's just going to set it to 0 to not lose anything. But if Q, yes, P and Q only represent the choice of one option, and you will use 1 minus P or Q for the other option instead of the other number to make it simpler. Yeah, basically. The reason we use P and 1 minus P is if we used P and then some other number, we would not be able to simplify it down to something so clean. So while in the short run, it's, looks nicer, in the long run, you do have to simplify it to something like this, and you will always be able to simplify it like this, but you have to use like a probability and then 1 minus that probability. So so that answers that question. And do you understand where we got 0.6 from? It's just look at the coefficient of P. All right, cool. So now that we have player A's response rules, so keep in mind 0.6, right? Just keep that in the back of your head, I guess. Now we move on to player B, right? So player B's payoffs are, so again, we do the exact same thing, but now with player B. So suppose we know that player A, suppose we do the little thought experiment. If player A necessarily has to go up, player B, I'm going to move this text box, player B will choose left with Q% chance and right with 1 minus Q% chance. Am I saying? Okay, I completely messed that up. Sorry. Left with Q chance and right with 1 minus Q chance. There's no percents. I'm not using percents. So that means that with Q chance, if player A goes up, player B will get 5. And with 1 minus Q chance, if player A goes up, player B will get 2. And similarly, if player A will necessarily go down, player B will choose left with Q chance, getting a payoff of 1, and right with 1 minus Q chance, which will net a payoff of 8. So yeah, then we can, again, so player B's payoffs are then 5Q plus 2 times 1 minus Q if player A chooses up, and 1Q plus 8 times 1 minus Q if player A chooses down. So does everybody understand how we got those numbers? I see one yi. That's good. So yes, yeah. Yeah, that's a new one. All right, and that's another nuance, satisfaction. Okay, so again, we know we know what player we don't know what player A's choices are, but we have the variable representation of player A's chances, right? Player A chooses up with a chance of P, and player A chooses down with a chance of 1 minus P. So now, again, like we did in the previous case, we just include player A's probabilities into player B's payoffs. So 5Q plus 2 times 1 minus Q times P, and then 1 plus 1Q times 8 minus 1 minus Q times 1 minus P. So again, there's a P chance that A chooses up, and in that case, with chance Q, player B goes left and gets 5, and with chance 1 minus Q, player B goes right and gets 2. There's a 1 minus P chance player A chooses down, in which case player B chooses, let's see, is that a question mark or an emoji? Because I just need the box, question mark in a box thing on my screen. Zoom doesn't like emoji. So that is a question mark. What's the question? Okay, that's good. So shouldn't the variable always be first in the equation? Yes, but just kind of, it's, I mean, if you want it to look nice, yes. Minus, it just makes it easier to read. Technically, yes, but in the end, it's just a style thing. It doesn't really matter. Okay, but okay, yeah. Is it possible to solve for P of Q, or if one's decision is dependent on the other's decision, which is dependent on the first person? Yeah, we'll get there. It's a bit non-trivial how we now. So again, we'll get there. Don't worry. We'll figure out how to solve for P and Q. So yeah. So again, we have this equation, and then we simplify that to 8 minus 6P plus 10P minus 7 times Q. So again, notice how there's only Q only has bearing over one place when P is in 2 locations. So we focus on the coefficient of Q, which is 10P minus 7. So when P is less than 0.7, the coefficient becomes negative. Sorry, I don't speak whatever language that is. If P is less than 0.7, the coefficient becomes negative, and Q should be 0, right? Because at that point, this is not large enough, and suddenly player B is losing payoff, so they say no, and they just make it 0. When P is greater than 0.7, the coefficient becomes positive, and Q will become 1. So player A will always choose left. Suddenly, player A is increasing their payoff with thanks to player A's choice. So they're going to say, okay, let's just put all of our things into that to always get some extra stuff. And when P is 0.7, player B will get the same expected payoff no matter what they choose, because if you plug in 7, suddenly the part that Q controls, has like a bit of control over, is 0. So it doesn't matter what player B chooses. So now we have both response rules for both player A and player B. Right. And you can probably intuitively guess, like, okay, so they both have a part that says 1, 1 equals 0.7, it doesn't matter, and 1, 1 part equals 0.6, it doesn't matter. So it's probably that overlap. But we're going to show this graphically, actually, in a very nice, clean graph. Okay, let's keep the chat a bit more on topic. All right, so we can solve this graphically, right? So these two graphs, so this first graph represents player A's response rules, right? So the x-axis is Q, which, if you remember, represents player B's chance of picking left, and P represents player A's chance of picking up. So as Q goes to 0, if Q is less than 0.6, P is 1, right? If Q is less than 0.6, P is player A is always going to choose up. If Q is greater than 0.6, P just goes down to 0 immediately. Suddenly, player A is always going to choose down, and then now, if it is exactly 0.6, it doesn't matter what P chooses. Similarly, we can do the same thing with player B's response rules, but for some reason they reverse the axes, which very much annoys me. I did not make this. Again, I stole this example from my textbook, and I agree with you completely. The axes are different, and that annoys me. But let's deal with it for a bit. So again, P is on, if P is less than 0.7, then Q is going to be 0. Remember, if it's less than 0.7, player B is losing payoff, so they're just going to never choose left. If P is greater than 0.7, Q becomes 1. So player B will be gaining payoff, so player B will always choose left. And if it's anywhere in between, if it's 0.7, Q will be anything, right? It doesn't matter. So now if we rotate this along x equal, if we mirror this along x equals y to just how do you do we just do the right, it's not a translation, it's a mirror effect, right? Because you can't see my hand. It's not a rotate either. You just have to switch the axes pretty much, and then you can see that they overlap right over there. So does everybody understand that? It's kind of a weird thing, but does everybody understand this? Other than the weird axes problem. So I see one, yeah, looks like one symbol. Hardy har. So I'm getting some understands. So are there any questions at all with, I don't speak Japanese. Everybody understand what's going on here? Any problems at all? Because again, I'm going to be showing something pretty interesting after this. So I think everyone's good. Kind of. So what is the probability stuff? Remember, this is just, Q just represents the chance that player B chooses left. 1 minus Q is the chance that player B chooses right. P is the chance that player A chooses up. And 1 minus P is the chance that player A chooses down. So that's what that means. But now that we have this intersect, we know what they should be doing. Is it more math, harder math, or easier math? I mean, it's not so much, I don't know. It's kind of weird. Because the math isn't probably the thing. No. So P is, in this case, 0.6, right? It's just the, so let's go back to the player A's response rules. So in this case, so as you can see, we have this, it's not an equation, I don't remember the word. But as you can see, player A's, let's go back a bit farther. Player A chooses up with P chance, and then down with 1 minus P chance, and then player B chooses left with Q chance, and then right with 1 minus Q chance. So in this case, so with this part, this is just player A's payoff, right? The expected payoff, but we don't know any of the probabilities, so we just have to create this expression, that's the word. So is there a problem again? So as you can see in this expression, geez, sorry, P is like player A has control, so P is but in the end, player B takes Q, right? So player A has to plan what he's going to do, what they're going to do based on Q, but they don't actually have any bearing over Q. So they have to, yeah. So any more questions? Let's just go to the very last slide again because it's a nice. Okay, again, let's just keep the, don't chat unless you have a question or a statement. Okay, if we're all good to move on, this is where the fun part starts, I guess. I don't know, not really. Everyone can still see my screen, right? Okay, cool, because I'm going to stop it for just a second. I don't know why I asked that. So give me a sec. I'm going to quickly pull some stuff up. I'll be right back. Don't do anything dumb, I guess. Okay, I'm still here. Let's share screen. Google Chrome, that one. Ta-da! This is my paper.
Nice.
Yes. This was my, so, oh yeah, I did it all just in like 2 seconds, exactly. No, this was my final paper for the class, for my game theory class. As you can see, I finished it May 27th, which is about when my school ended. I don't remember, this was, I didn't submit this on the last day. So this is just, so I'm going to, so one of the many applications of game theory in like real life right now is in sports, right? So so there are several sports in which you can look at. So I covered tennis, but previous years, some guy covered football. You know, the running team can either play offensive or I don't play football. Some different various strategies, and then the defensive team could either do one thing or another. And usually there isn't a Nash in there, right? So you have to, in sports, most of the time there's a mixed Nash equilibrium. Neither player has pure strategies, so you need to. No, you cannot do this in swimming. So both you need to figure out what the mixed Nash equilibrium is, and in this case, I decided to do it over tennis serving. So with serving, whenever you're analyzing a game, like a real life game, you have to very heavily simplify the game, right? You have to make a ton of assumptions. You have to make it simpler. Otherwise, there's just going to be so much going on that it's just going to be like impossible to think about. So in this case, I made a few assumptions. So first of all, I mean, you can read it if you want. It's long and it's annoying, and it's 7 pages somehow because there's tons of charts for no particular reason. But the few assumptions I made were that, first of all, when one player is serving, the other player has to like react immediately, right? So I assume that when serving, it's a simultaneous game. So the person who is serving cannot react to the person who is returning, and the person with, no, I did not. That was a joke. I shared this with my teacher and he didn't laugh at the title. But so the person who's serving can either cannot react to the person who's returning the serve, and the person who's returning the serve cannot react to the person serving. So they both have to make their decisions that instant, right? Another assumption I made, that was kind of fast. So another assumption I made was that both players, there's only like 2 parts of the serve box per se. So you can either serve to the left or you can either serve to the right. Or in tennis, let me just pull up a picture of a tennis court. No, not a tennis court near me, just a tennis court. So sort of nice, yeah. So I'm just going to pull up a tennis court real quick. So if this guy is serving, he can, there's this net down the middle, so he can either serve towards the edge, which is just going for the alley, which is, this is the doubles alley. So going towards the edge is called the doubles alley. And then if you want to serve more down the middle, that's called going down the tee, because like, remember, there's kind of a net here. So if you just look at one half of the court, then this kind of forms a T. So going down the T is going down the middle. So that's the other assumption I made. So I analyzed a specific game, just some random one I found on YouTube. I pretended like I picked it for a reason, but honestly, I picked it because it was short. But so another, probably the most important assumption in this I made was that the serve. So again, it's not super hard to come up with that simplification of going to the left or to the right, right? That's like a natural thing, and that's actually not a super large generalization. The interesting part is payoffs. If you remember back to the day we talked about sequential games and the chessbot, the hardest part about the chessbot is deciding how it should allocate payoffs. And in the end, that's what's, if you're doing more basic game theory, that is the interesting part, choosing payoffs in order to create a game that's to just create the game. So in this case, I used like the percent chance of a player winning if that specific outcome occurred, right? So lots of words that are probably fun to read. But so players are Federer and Djokovic, for any of you who play tennis. So this just means going for the both. So that means, which one was serving again? I don't even remember. I think Federer is serving. Yeah, so Federer is serving and Djokovic is returning. So another thing you have to do is that if you, again, have to continue to simplify the game. Yeah, if you're simplifying the game, you have to like just make it, narrow it down. So I only looked at the case where Federer was serving. And so, yeah. So this is one example. So again, we can't look at deuce in the ad side. Yeah, Djokovic is a word. It's weird, so many consonants. But if we're only looking at one side, remember, tennis players change sides. So we're only looking at the side where I'm on the right. Really? I didn't know that kind of person existed. So if Federer serves to the alley, remember, so he's serving like far out. He's going for the edge. And Djokovic also thinks that like reacts. He goes towards the alley. Then this is the chance that a player will win, right? And so that's what this means. So I decided that payoffs should be based on, in a given scenario, what is the chance that each player will win? So yeah, another aspect about tennis that's kind of interesting is that there's a double fault system. So if a player faults, suddenly they move on to the second serve. And, second serves are usually pretty different from first serves. So I actually like separated games that only had first serves and games that had first and second serves. And I eventually put them back in there together. So, right, if you want to look at the very final things, here we are. This is a very lengthy game table, right? So as you can see, this is a constant sum game. If you remember let's just random check. Who remembers what a constant sum game is? Okay, I see one me, and I assume everybody else is just typing me. Yeah. Okay, so the percents represents the chance a player is going to win at a given point. So just focus on these tables. The other tables are confusing, and you need to read my paper, and it's not fun. It's a not fun paper to read. Yeah, I had a very severe leak while writing this, and don't worry. So, how many words? I don't know. Tools, word counts. A lot. Oh, wow. That's a lot of words. This took me a long time to write, but this is the kind of stuff, if you find your own game theory class at school or something, this is the kind of paper you're going to write. But so these payoffs just represent the chance of each player winning. So if Federer serves to the like edge, then he's going to win with like 1/5 chance. And if Djokovic predicts that that's where he's going, then he wins 4/5 of the time. And if Federer goes down the middle, and Djokovic also predicts he's going to go down the middle, Djokovic just always wins, which is pretty interesting. Yeah. So So if you notice that Federer isn't playing very well, and he did not at all, so you can in this game you can calculate the mixed Nash equilibrium, and you discover that Federer really wasn't following it. He was playing very poorly, and he was just messing up constantly. Not only was he playing badly, he wasn't even like acknowledging that he was playing badly and changing how he played, which is pretty interesting in itself. And now we do the same for the ad side, and it's a bit different. It's a bit more balanced, but yeah, in the end, yeah, Federer just played incredibly poorly. So yeah, I'm trying to think if I'll get a bit deeper into this. So first, you know what? The second half, of, like the last 5 minutes, I thought that my slideshow would be a bit longer because I have a lot of math. So I'm just gonna quickly. Here's our mini lesson on how to write a game theory paper. I did. Oh my god! Writing this took a while. So if I guess this is also just a general thing for school. Writing papers takes a while, and good papers take a while. So first, you need an introduction, obviously. But the first bit of the game theory paper, you need to describe how you're determining things, like how am I determining payoffs, how am I simplifying the game, how am I creating my game table, and what moves can players choose, right? You just need to define what's going on. If you remember back to I basically say this every day for various reasons, but the most important part of a game theory problem is actually defining the problem, right? Solving, there are methods for doing it, but the hardest part probably usually is actually defining what you're doing. Yeah, you're establishing your keys and what you know. Exactly. You define what you know and what can happen. And you also need to define what you're searching for. So I think I kind of formatted this poorly because there's this massive table. So then you need to compile your data. Compiling your data is, this took so long because I had to watch like an hour of tennis and just write down who won games and how did players like react to serves and stuff. So that took a while. Uh, uh, it was an experience to say the least. It was fun. I like you kind of after watching a lot of tennis, you get in the zone. Sucks to be me. Yeah, it did. It took so long and it got so boring. But yeah, that's part of game theory. You have to get used to it. Some like all the fun part is like the math and the actually doing stuff and learning. The not fun part is just slogging through data. That's the annoying part. Not even data. Like slogging through data on this part wasn't even the worst part. Slogging through the worst part of this was slogging through a tennis match and try analyzing. So it's pretty obvious. Yeah, most swim races take under 5 minutes exactly. But in a tennis match, so not only do I have to determine, it's pretty easy to determine, which side is the guy serving to, but it's a bit more difficult to determine what is the player going to is the returner Djokovic, let's see, going to go left or is he going to go right? And you have to analyze his foot patterns. And I mean, I wouldn't be able to do this if I didn't know tennis. Did your class last a whole year or like half a year? This it was a half-year class, but I did some extra stuff. So for me, it was a bit more than that. But yeah. Yeah. What the? Jeez, there's just so many distractions going on in my room. So yeah, ding. The great thing about my class is that because of all this COVID-19, I didn't have a final. This was my final paper. The guy just my teacher. He's a cool teacher. He just said, okay, don't worry, just write a paper instead of having a final exam. Actually, it wasn't instead. Usually in my class, seniors get to choose between a final paper or a final exam, but everyone who's not a senior has to do both. And I would have done both, but then this happened, so I only did a paper. So. Yeah. So yeah, you have to define what's going on. Hey, look, probability, fun. you guys recognize that, except I didn't define any of those for you, so you probably don't know what that is. Math, math, just lots of math. And then you compile the game table finally, and then you have conclusions. Then the last paragraph is usually, why does this secretly suck, and what did I not do well? So, yeah. I guess ask any questions about game theory classes and papers in general. Um, I don't know. All right. No. I like having this. My equations look funky. Uh, that's because I'm not using LaTeX or LaTeX. I don't know if it's LaTeX or LaTeX. But yeah, these aren't actually at all different from what we covered in the slideshow. It's just that because this, I just use, this is the exact same thing, right? It's just weird numbers, right? How did I do on it? I got an A, which I'm very proud of. So yeah, like let's take a look at this, right? This is the exact same. AOPS, people know LaTeX. Yeah, exactly. But I can't write in LaTeX because I didn't know how, I didn't think my teacher would accept a paper in LaTeX. So yeah, but in this equation, right, it's the exact same in the end. In my school, it's an elective class, so like it's not a mandatory class now, but you can choose to take it. But it's not a club because I also get a grade on it. So yeah. So if let's do a fun little exercise. If you had to do a game theory paper like this, what would it be about? And remember, it has to be. I mean, it can be anything really. Um, what textbook? I'll put it in the ed thing like today. There's a textbook that we use. Yeah. Can it be a story? Perhaps. This was mine. I did mixed Nash equilibria, but several people have just made like absolutely massive sequential games that were just huge game trees. Um, so yeah, it could be a story. Yeah, football you could do. Um, yeah. Okay, so I'm just gonna stop here. So, um, thank you. Could you do basketball? Probably, yeah. Probably have to simplify it, maybe like a penalty shot. You couldn't do all of it. You could do a little mini bit of basketball, right? In my tennis game, I didn't do all of tennis. I just did the serve. So yeah, yeah. You have to work hard no matter what the topic is, unless you decide not to, and then you'll probably get a bad grade. But thank you all for coming. We'll see each other. Today is Tuesday, so we'll see each other Tuesday and Thursday. So yeah. Have a good tomorrow, and I'll see you the day after that good tomorrow. So, bye.